Hello everyone. So in this session we will be starting carboxylic acid and its derivatives. So I'll be covering this chapter in mainly two parts. The first part, which is going to be the theory part, or which happens to be the part which will be mainly from NCERT, will be discussed first. Later we'll move on to the problems, and when we will do problems, the extra concepts that are required which are not given in NCERT, I will discuss it there. But as we all know that NEET and all other exams, all other medical exams are mainly based from NCERT. So my majority of the priority will be in discussing that theory which is specifically given in NCERT in detail. So let's begin this chapter. So the first thing that comes into our mind is, what is a carboxylic acid? So to answer what is carboxylic acid has been defined as carbon compounds containing a carboxyl group. So now we have to pay attention here to what is a carboxyl group. Carboxyl group is actually the C double bond O OH group, or which can also be written as COOH. When it is written as COOH, how you will understand that there is one oxygen that is doubly bonded with carbon, and there is one oxygen that is singly bonded with carbon, and there is a hydrogen atom. So when you analyze that what this carboxyl or why this group is known as a carboxyl group, then if I just divide it into two parts, I can say that a carboxylic group can be assumed to be made up of a CO part and OH part. We know the groups which contain CO part is actually known as carbonyl, whereas the compounds containing OH or OH group is also known as hydroxyl group. So we can say when we are saying carboxyl group, it happens to be due to, since it is made up of carbonyl plus hydroxyl, together they are known as carboxyl groups. Now depending on whether this carboxyl group is attached with the alkyl part or it is attached with aryl part. Aryl will be an aromatic system. This will be known as either aliphatic carboxylic acids or when the COH group is attached, or when the carbon of the carboxyl group is attached with an aromatic system, then this will be your aromatic carboxylic acids. So now where we know that R part here is the alkyl part and AR part here is aryl part. I hope you know what is actually an aryl part, a substituted phenyl system, or if I write only C6H5, C6H5 is known as phenyl, whereas if this C6H5 system is attached with anything else also, then this will be named as aryl. So basically the idea is, if the carbon of the carboxyl group is attached with an aromatic system, we are going to call it as aromatic carboxylic acids, or when R part is aliphatic, we will call it as aliphatic carboxylic acids. So I hope now we are clear with the part like what are carboxylic acids. Next thing that you can see is derivatives, which I can write or which I can abbreviate it as CAD, where C stands for carboxylic, A for acid and D for derivative. So now if we try to define what are carboxylic acid derivatives, now carboxylic acid derivatives are, these are compounds containing those functional groups which on acidic or basic hydrolysis, will produce carboxylic acids. So once again, if we read the definition, like what are carboxylic acid derivatives? Carboxylic acid derivatives are those compounds which contain such functional groups that if they are hydrolyzed, for hydrolysis we can use acidic medium, we can use basic medium also. If we do the hydrolysis of those functional group, they are going to produce carboxylic acid. So now I am going to write some of the most important carboxylic acid derivatives, which are going to be, first I can write RCOX, where X can be chlorine, bromine, iodine, anything, but it is mainly chlorine and bromine. This is known as acid halides. This is one of the carboxylic acid derivatives. Another one will be RC double bond O, C double bond O, R. This functionality is known as acid anhydride. Acid anhydride. After this we have RC double bond O, R, where R can be the hydrogen part, can be the alkyl part, or can be the aryl part as well. This functionality where RC double bond O, OR is attached, this is going to be ester. Then another carboxylic acid derivative will be RCONH2. This will be known as amide. Now don't get confused this amide with NH2 minus, because in chemistry both of them are actually known as RCO. NH2 is also known as amide, NH2 minus is also known as amide, but you will get to know which one they are actually referring to. Another carboxylic acid derivatives will be RC triple bond N, which is known as nitriles. So if I go with the definition again, I am saying that all these compounds are actually carboxylic acid derivatives. That means that if any of these compounds are subjected to hydrolysis, hydrolysis means treating them with water, which will be catalyzed by H plus. H plus here stands for the acidic medium, or OH minus, which represents basic medium here. All of them should be hydrolyzed to the carboxylic acid. All this will be hydrolyzed to the carboxylic acid when medium is acidic. Whereas if we are doing hydrolysis in the basic medium, so I can write it in a better way, I can say this hydrolysis when will be catalyzed by an acid H plus, the final product will be RCOH. Whereas if the hydrolysis of these compounds will be catalyzed by a base, then the final product will be RCOO minus, which is known as carboxylate. And here itself I want you to make a note which is very important for understanding the basics, that in a basic medium acid cannot remain protonated, because acid and base are like enemies of each other, which are going to kill each other or which are going to definitely react with each other if they are present together in the solution. So, that is the idea, that whenever you are writing carboxylic acid and it is formed as a product in the basic medium, then basic medium will make sure that to take out its hydrogen. Or you can say in basic medium, the carboxylic acid will always stay as carboxylate. A very important point, a very basic point which all of you must see, or while going through the theory in NCERT, you will observe that whenever carboxylic acid was produced in the basic medium, they always wrote it as carboxylate. Whereas neutral or acidic medium, carboxylic acid can remain in the protonated form and the final product directly itself will be RCOH. So, if the medium is basic, final product will be carboxylate. Whenever carboxylic acid is produced in the basic medium, it will require an additional step which is known as protonation, or you can say workup. This workup step is done to get a neutral product which will be carboxylic acid. Fine. So, in basic medium, if you are preparing a carboxylic acid, you will never get carboxylic acid directly. You will get a carboxylate ion which is formed in the basic medium, which will require its protonation to form carboxylic acid. So, I hope now you are clear with the idea what is a carboxylic acid, what are its derivatives. One more thing that you guys can actually observe is, when you say carboxylic or when you say carboxyl group is actually made up of carbonyl and hydroxyl, it never means that the properties of this carboxyl group will be an average of the two. Or what I am trying to say here is, you are not going to make a statement that carboxylic acid will have some properties of carbonyl compounds and some properties of hydroxyl compound. What exactly happens is, when you actually write a carboxyl group, it is completely different from the carbonyl as well as hydroxyl group, and it shows its distinct properties. So, carboxylic group has its own distinctive properties which we will be discussing through the course of this reaction, through the course of this chapter. So, now some other general thing that we can discuss here is, your carboxylic acids can be classified as mono, di or tricarboxylic acid depending on number of COH groups present. For example, if I have CH3COOH, we are going to call it as monocarboxylic acid. If we are having another compound which is CH2, C double bond OH, C double bond OH, or let me write it as CH2 COOH. This contains two carboxylic group. This is actually our dicarboxylic acid. And similarly, we can write another compound which will be having three COH groups, which will be tricarboxylic acid. So, carboxylic acid can be classified into mono, di or tricarboxylic acids depending on how many COH groups are present. Now, if you see the saturated aliphatic carboxylic acids forms a homologous homologous series which is having the general formula CnH2nO2 or CnH2n plus 1 COOH. The higher members, that is C12 to C18 of saturated aliphatic acids are also known as what? Fatty acids. So, what are fatty acids? Fatty acids are the long chain saturated carboxylic acid as they occur in natural fats as esters of glycerol. So, you should remember, if someone says what are fatty acids are nothing but the long chain of aliphatic carboxylic acids as they occur in the natural fats as esters of glycerol. Now, what we can do is, sometimes the carboxylic acids are said to be derived from alkane by replacing a hydrogen and adding a COH group, and you will get the corresponding carboxylic acid. For example, if I consider methane, and from this if I am removing an hydrogen, then I will get CH3, and if I add a COH group, then this will become CH3, C double bond OH. So, I can say from this, if I consider that replacing the hydrogen atom of an alkane produces acid by substituting hydrogen for a COH group, this will give acetic acid. Similarly, if I write CH3 which is ethane, and if I replace a hydrogen of this plus COH I add, then it will become CH3, CH2, COH, and this will be our propanoic acid. Now, one thing that you can see here is, one limitation will be that you will not be able to relate formic acid with any of the alkene, because formic acid has only one carbon and you will not be able to relate it with any alkane. So, some people try another classification which is actually based on oxidation and which you should also know. So, the another classification says that if you take the most reduced state of carbon, it will be as CH4. In CH4, if I try to count the oxidation state of carbon, then I can say, since electronegativity of carbon is greater than electronegativity of hydrogen, so I can say when I am going to break this bond, carbon will get -1 and hydrogen will get +1. Like this, on cleavage of all the 4 bonds, I can say carbon is actually present in the -4 oxidation state. If I do stepwise oxidation, then methane on oxidation to only one step will produce alcohol of the formula CH3OH. CH3OH is an alcohol. So, alcohols are the first oxidation product of alkanes. And again, if I see in terms of physical chemistry whether its oxidation state has increased or not, I can find it out by finding out its oxidation state. So again, if you break these 3 bonds, then the charge should come will be -3. And if you break a bond between carbon and oxygen, we know that the electronegativity of oxygen is greater than that of carbon. So I will get +1 and -1 on oxygen. Adding the overall charge on carbon, you will say, sir, oxidation state of carbon here is -2. So -4 to -2, that means it has lost 2 electrons. If alcohols are the further oxidized, then they will be oxidized to HC double bond OH, which is actually an aldehyde here, or you can say a carbonyl compound. So this will be formaldehyde. When this is oxidized, oxidation can again be confirmed by finding out its oxidation state. Cleaving these 2 bonds will give a -2, cleaving these 2 bonds will give a +2 on carbon, leaving overall charge as 0. So I can say in HCHO, the oxidation state of carbon will be 0. Now if it is further oxidized, here I am doing stepwise oxidation, what we are going to get will be formic acid. And in formic acid, if you calculate the oxidation state the same way, then you will get it as +2. And formic acid can then further be oxidized to carbon dioxide, where oxidation state of carbon will be +4. So using this idea, you can say that formic acid is actually the third oxidation product of alkane, or carboxylic acid will be the third oxidation products of alkane, because this is, I have shown stepwise that alkane will be first oxidized to alcohol, alcohols to aldehydes or ketones, then to the corresponding carboxylic acid, which if further oxidized will be oxidized to CO2. So this is another classification which you have to see, or organic transformations are mainly based on this idea only. If I ask if we have an alcohol and if we have formaldehyde and if we have an alkane, you should be able to tell me which is more oxidized form and which is less oxidized form compared to the alcohol. So I hope this classification will be okay here. After this, we can actually move into the nomenclature part of carboxylic acid. Since carboxylic acid compounds happens to be the first among those compounds which were discovered very early, an earlier system of nomenclature was actually based on common or trivial names, and those common or trivial names were actually based on the source from which that particular compound was isolated. For example, HCOOH is actually isolated from which source? It is actually isolated from ants. The Latin word for ant is actually formica. And how their common names were replaced? You add an ic to the common, you add ic to the Latin name of that particular compound, you will get the common name or trivial name of that particular compound. So here the common name that was given to HCOH was formic acid based on its source of isolation. And how did we name? The Latin name of that, and we added ic into that. Similarly, if I talk about the another acid which will be CH3COOH, which is actually isolated from vinegar. The Latin for vinegar is acetum, and how its common name will be derived? Just adding ic to this, and that will be acetic acid. Next one will be CH3, CH2, CH2, COH, which is actually isolated from butter or rancid butter, where the Latin for butter will be butyrum, and adding it to this will be butyric acid. Similarly, pentanoic acid, which will be CH3, CH2, 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 COH, it's isolated from the roots of valerian plants, and that is why the names valeric acid is given to this. So, what is more important for you is remembering the common names of the corresponding acids, because you need to remember their source also as it's given in the NCERT, and you need to remember their common names also, because sometimes in question they may not refer to them by their IUPAC name, rather they can choose the common names. So, this thing is important from kind of framing questions which are mainly based on informations. So, this was the common system of nomenclature, whereas when you talk about the IUPAC system of nomenclature, they name it as, if you have an alkane, from an alkane you can remove its E and you can add ic to that, and you will get the name of the acid. For example, if I try to write the IUPAC name of HCOH here, that will be methanoic acid. So, I removed E from the alkane and I have added oic acid. Similarly, this will be ethanoic acid. Next one will be butanoic acid, and the last one will be pentanoic acid. So, IUPAC system of nomenclature I am not going to discuss much, as it will be already discussed with you. So, we will just leave it up to here itself. Next thing that we can discuss is electronic structure of carboxyl group. So, next thing that we have is electronic structure of carbonyl group. So, if I make the basic framework of carboxylic acid, then we know carbon is doubly bonded to one oxygen and singly bonded to another oxygen. If I talk about the state of hybridization, then the carbon atom in case of carboxylic acid is sp2 hybridized. The hybridization of this oxygen as well as this oxygen is also sp2, and all the bonds are in plane. That means this bond and this bond, all the bonds are in plane and at an angle of nearly 120 degree. Now, one more thing that we can see here is, this is about the structure, and now let us try to understand what is the electronic arrangement. If I look into this carbonyl part, that means this part in particular, then I know there is a multiple bond between carbon and oxygen, and we all know that the electronegativity of oxygen is greater than that of carbon. As a consequence of which, I can say that this pi electrons will be shifted towards the more electronegative atom, and as a consequence of that, what will happen is, it can polarize the double bond towards itself, which can be written as O minus. Carbon will get a positive charge and there is a lone pair on this oxygen. In case of carbonyl compounds, carbonyl compounds used to undergo nucleophilic attack, because nucleophiles are the species which are rich in electron and they want to attack the substrate which carries the positive charge. Here also I can say due to positive charge, the carboxyl group will also have a tendency to undergo attack by a nucleophile. But there is a trick here. This positive charge on carbon which is introduced by this oxygen by polarizing of this multiple bond is diminished due to the plus M effect of this OH group. Due to this plus M effect on OH group, what it does is it neutralizes the positive charge so created on carbon. So, as you can see, due to the plus M effect, this positive charge has been neutralized, and due to this neutralization of positive charge, by which factor? By plus M effect of OH makes a carboxylic acid less reactive towards nucleophilic attack compared to aldehydes and ketones, as aldehydes and ketones do not have any group directly attached to the carbonyl carbon which can actually decrease electron density by plus M. Therefore, if I write an aldehyde or a ketone, that will be HC double bond O, it can be any R group, or ketone will be RC double bond O R. So, the positive charge that will be created in them will be more intense compared to carboxylic acid. So, here you can say this positive charge is more intense compared to a carboxylic acid, as in carboxylic acid it is neutralized by plus M effect. So, if I am considering the reactivity of carboxylic acid towards a nucleophilic attack, I can say wherever there will be a more positive charge, reactivity should be more there. And as you can see, positive charge is more on aldehydes and ketones compared to carboxylic acid. So, if you are comparing the rates of attack towards a nucleophile, then you can say carboxylic acids are less reactive. So, this is what I wanted you to understand here from the electronic structure of carboxylic acids. Next thing that you can have is dicarboxylic acids. You can know some of their names, common names and to be very particular. The shortcut for remembering the dicarboxylic acid is Ohm's gap, or some people prefer to remember it as "Oh my son, go and play," or "Oh my sweet green apple." It depends how you want to remember it, and it actually starts from the dicarboxylic acids are actually represented with a general formula CH2N COOH COOH, and the value of N that you start from, since it starts from O, you remember this is 0, this will be 1, this will be 2, this will be 3, this will be 4 and this will be 5. So, if I make it structures, what I can write here is, I can say when N value will be 0, there will be no CH2 group present in between the carboxylic acid. So, they will be directly attached. So, this acid I can say is the oxalic acid, When N value will be 1, the structure will be CH2, COH, COH, and when N is 1, the name should start with M, that should be malonic acid. When N value will be 2, the name will be CH2, CH2, COH, COH. So, when the N value is 2, its name has to start with S. So, this acid is succinic acid. When N value will be 3, the structure will be somewhat like this: CH2, CH2, COH, CH2, COH. When N is equal to 3, its name has to start with G. So, it has to be your glutaric acid. And similarly, you can write A and P also, where A will stand with adipic acid. For adipic acid, number of CH2 group has to be equal to 4. So, we can make it as COH, COH. So, number of CH2 is 1, 2, 3, 4, and with 5 it will be pimelic acid. So, this dicarboxylic acid, sometimes they will directly give a question succinic acid, then you should know what is the structure of succinic acid. Other than these acids, what you should remember will be your lactic acid. Lactic acid here will be a carbon connected with a COH group, connected with a CH3 group, connected with an OH, connected with an H. On the other hand, the citric acid will be one CH2COH group on this side, one CH2COH group on the other side, and one COH group and one OH group. So, this will be our citric acid. Another one that you should remember is phthalic acid, which is benzene 1,2-dicarboxylic acid, which will be carboxylic acid at ortho position relative to each other. So, there are few common names that we will be requiring for solving problems. So, you should know their common names as well. So, this is where the general introduction part will end, and now we can actually go into the methods of preparation. So, in methods of preparation of carboxylic acid, the first one that we are having is from alcohols, or mainly from primary alcohols. Primary alcohol can be represented as R CH2OH. Now, this can be oxidized by using potassium dichromate, which will be K2Cr2O7 in acidic media. This primary alcohol can be oxidized using KMnO4, hot KMnO4 in neutral, acidic or alkaline medium, or the oxidizing agent that can be used here will be your Jones reagent, which will be chromium trioxide in the presence of an acid, let us say H2SO4. So, all these are strong oxidizing agent, and what they are going to do is this carbon to which the OH group is directly attached will be oxidized. So, if I make it as a star, then what these groups are going to do will be, they are going to oxidize that carbon into carboxylic acid. So, it is the carbon of the alcohol which is now oxidized to carboxylic acid by oxidation. So, you can say how to prepare carboxylic acid from alcohols. As I already told you in the beginning that carboxylic acid will be the second oxidized product from the alcohol. So, first method is oxidation. Now, why only primary alcohols? Why can't we use secondary alcohols? You have to make a note here is, what will be that note? Is if I am having a secondary alcohol requires the carbon to which OH group is attached must be attached with two more alkyl group. So, I can say this is a secondary alcohol. If I oxidize this, if I do oxidation of this secondary alcohol using any of the above oxidizing agent, then you will understand that secondary alcohols are first oxidized to ketones. And ketones under normal condition are not further oxidized. So, the reaction stops at ketone stage itself and the final product for the oxidation of secondary alcohol will be ketones itself. If you can see the difference between them, then you will say there is a hydrogen removed. This hydrogen if you remove, you will actually make a double bond between carbon and oxygen. That is why the oxidation of alcohol to ketone is also an example of dehydrogenation reaction. D means removal, hydrogenation means of hydrogen. So, now you are someone like who knows that anything can be possible in chemistry. So, you are saying no sir, I want to oxidize ketones further to the acid. That can only be done by the oxidative cleavage. That means, if I am having a ketone, let us say CH3, C double bond O, CH2, CH2, CH3. Let us say this is a ketone which is 2-pentanone. There are 1, 2, 3, 4, 5 carbons. Let us say you are treating it with strong oxidizing agents like concentrated nitric acid, or if you are using hot KMnO4. Let us say you are using it in hot alkaline KMnO4, or let us say you are using another strong oxidizing agent which is potassium dichromate, and let us say you are using it in the acidic medium. Then under normal conditions, none of that oxidizing agent actually oxidizes ketone further. But if you make your conditions vigorous, then what happens is it brings out the oxidative cleavage. And on oxidative cleavage, what happens is the carbon gets oxidized to carboxylic acid. And for this, we have to use something called Popov's rule. In Popov's rule, what we say is the carbonyl part of a ketone will go with that alkyl part which contains fewer number of carbon. If I consider this as a carbonyl, then this is actually the alkyl chain. So, this side alkyl chain is only of 1 carbon and that side alkyl chain is of 3 carbon. So, oxidative cleavage means either this bond is going to break between alkyl part and carbonyl, or this bond will break between alkyl and carbonyl. If this bond breaks, then this carbonyl part is going to go with the alkyl part which has less number of carbon, and if you are breaking this bond, then this alkyl part will be separate and this CO will go with that alkyl part. Whereas Popov's rule says that this carbonyl, if I make it as star, is going to go with that alkyl part which has less number of carbon. That means only this cleavage will happen because the CO part will go with that alkyl part which contains less number of carbon. So, oxidation product here will be CH3, COOH. Let me mark this carbonyl as star. So, this is COH plus the alkyl part carbon which was directly attached to carbonyl will also be oxidized to carboxylic acid. So, what we have learnt is, in general, if you want to prepare carboxylic acid, what we employ is, we employ only primary alcohols, as primary alcohols can be easily oxidized to carboxylic acid using any of these three reagents, whereas secondary alcohol cannot be directly oxidized to carboxylic acid under normal condition because reaction stops at ketone stage which are not undergoing any further oxidation. But still, if you are very much curious, you want to oxidize it, then you can use strong oxidizing agent and actually cleave the carbonyl group or cleave this ketone according to the Popov's rule. Next will be from aldehydes. Let us say if I am having RCHO, this aldehyde can be oxidized to the carboxylic group RCOOH. If you see here in aldehyde as well as in carboxylic acid, the number of carbon atoms are same. So, this can be achieved via oxidation. And what are the reagents that you can use? You can use strong oxidizing agents as you used earlier, that is acidified. Potassium dichromate will also work here, or if you want to use hot and alkaline KMnO4, that will also very well do the job here. Whereas you can also employ mild oxidizing agents like Tollens reagent. How to identify a Tollens reagent? If you are given Ag2O, or if someone gives the silver amine complex, because it is ammonical silver nitrate solution, then also you should understand, okay, Tollens reagent is given. This above oxidation can also be carried out using Fehling solution, or you can use Benedict solution. As you know, all these are mild oxidizing agent which you might have learnt in carbonyl chapter of aldehyde and ketone. So, from aldehydes also, by oxidation you can use mild oxidizing agents, you can use strong oxidizing agent, all will do the job. Whereas with ketones, mild oxidizing agents are not going to work, even the strong oxidizing agents works only under very harsh conditions. So, this is from primary alcohols and aldehyde, how to prepare carboxylic acid. The next method of preparation is from alkyl benzene. In this particular case, it is mainly used for the preparation of aromatic carboxylic acid. For example, let us say if I am having toluene, this is CH3, then I am having CH2, CH3. Let us say our next example is CH, CH3, CH3, and the last one will be CH3, CH3, CH3. So if you see, what I have done here is, I actually took a primary alkyl, secondary alkyl or a tertiary alkyl benzene here. When this, I am referring primary, secondary, tertiary only with respect to the alkyl part. So if you do their oxidation using strong oxidizing agent, let us say hot alkaline KMnO4, or you are using, let us say, acidified potassium dichromate, then irrespective of the number of the carbon atoms in the alkyl chain, it is the carbon right next to the benzene where you have to focus. Let me highlight that carbon. It is the carbon which is just attached with benzene which you have to focus. So, irrespective of what is the alkyl part, this carbon, as long as it has alpha hydrogen, that means as long as this carbon is having hydrogens attached to itself, this carbon will be oxidized to benzoic acid. So, this carbon is having hydrogens attached to it. So, this will be oxidized to C double bond O OH. Similarly, again this is ethyl benzene. So, here you can see this carbon atom is what you have to focus. Irrespective of how long this carbon chain length is, if this carbon contains a hydrogen attached to it, then if you are using the above set of reagent, then here also your product will be benzoic acid. Again coming to this case, in this case again you have to focus on the carbon which is directly attached to the benzene ring. Then here also, as long as this has carbon, all other bonds will break and this carbon will be oxidized to benzoic acid. Whereas, if you are having a tertiary butyl benzene, in this particular case if you observe, then this carbon is not having any hydrogens attached to itself. That is why if you use the above set of reagents, then in this case no reaction. So, you should understand benzoic acid can be prepared from alkyl benzene only if the benzylic position is having hydrogens attached to it. If it does not have any hydrogen here, then those kind of alkyl benzene will be inert to oxidation. So, this is an important reaction which you should remember, and this example happens to be important for you. And this reaction is not only limited to your alkyl benzene, rather if you have a properly substituted alkenes, alkynes, you have a carbonyl, all of them can be oxidized to benzoic acid using the same reagents. For example, if I have something like this for you, let us say you are having benzene ring with CH double bond CH2. This, if you are using, let us say, hot and alkaline KMnO4, in this case also this carbon will be oxidized to carboxylic acid. So, we will get COOH. Not only this, let us say if I am having a substrate like this, C triple bond CH, using the above set of condition, again this carbon can be oxidized to benzoic acid. Now, some of you may wonder, sir, there is no hydrogen attached to this carbon. The condition of the hydrogen present at this carbon is only there for alkyl benzene, and that condition is not valid when it is alkene or alkyne. Other substrates, like if you are having CHO, which will happen to be your benzaldehyde, again if you are using the same set of condition, you will get benzoic acid, or let me write it as acetophenol CO CH3. This can also be oxidized to benzoic acid. So, this reaction is not only limited to alkyl benzene, but can be extended to properly substituted alkenes and alkynes. Next method of preparation that we are going to discuss will be from hydrolysis of nitriles and amides. Hydrolysis is once again the addition of water only. For example, let us say if I am having an alkyl cyanide RC triple bond N. This cyanide can be hydrolyzed using an acidic medium or a basic medium. Let us say I am using acidic medium. Then this nitrile is first getting hydrolyzed to amide RCONH2. And which still further gets hydrolyzed to the corresponding carboxylic acid, and ammonia gas will be liberated. So, if you are doing the hydrolysis of nitriles, so this hydrolysis of nitriles, if you maintain milder condition, milder conditions, then reaction can be stopped at amide stage. Let us say it is written that the conditions are milder and they are hydrolyzing your nitrile, then you can actually get amide as the product. Whereas under harsh conditions, or it is not given mild conditions and all, then nitriles will be directly oxidized to, nitriles will be directly hydrolyzed to carboxylic acids. Now, if you can see, nitriles as well as amides both on hydrolysis are producing carboxylic acid. So, these are the derivatives of carboxylic acid. I will give you the mechanism, but before giving you mechanism, hydrolysis is nothing, you just have to break the bonds between hydrogen and oxygen. For example, if I am having R, C triple bond N, you should know the polarity of this bond. You know that the electronegativity of nitrogen is greater than that of carbon. Nitrogen is more electronegative than carbon, due to which I can say this will get a partial negative charge and carbon will get a partial positive charge. Hydrolysis means breaking the bonds of water. So, I have H and OH. I know here also that due to difference in electronegativity, this will be the charge separation. So, all you have to do is you have to break these three bonds using hydrolysis. For that you will require 3 moles of water here. And how you will orient your water? You will orient it in such a way so that the negative part is with the positive part of the nitrile and the positive part of the water is with the negative. So, that is the perfect match of polarity. So, this will be OH, H, this will be OH, H with the charge separation delta positive and delta minus. So, break these 3 bonds and break these 3 bonds. Then what you will have here is, you will have R, C, and this 3 bonds will break, which will be formed with OH, OH and OH. This species is going to be unstable, as 2 hetero atoms on the same carbon are not stable. So, this is going to lose water, water will be OH and H and will result into the formation of carboxylic acid. Whereas, this N minus will be connected with 3 hydrogens, which will be ammonia. So, this is the complete hydrolysis of nitrile to carboxylic acid and ammonia. If you stop it at intermediate stage, then you can actually form amide also. Let me give you the mechanism in the acidic medium. Let us say I am having R, C triple bond N. I know this nitrogen has 3 bonds, so it has a pair of electron. I am writing the mechanism in the acidic medium. H plus here is the electrophile which attacks the site of more electron density in the molecule. And as we can see, there is a lone pair. So, this lone pair will be first donated to this H positive. The attack or the direction of arrow is always from nucleophile to electrophile. So, after attacking on the lone pair, this carbon nitrogen bond can be written as N positive H. I hope you all know whenever a neutral species donates electron, after donating it gets a positive charge. So, this hydrogen after attaching itself to nitrogen has actually increased the electrophilicity of this carbon. Just try to think that this carbon was already polar due to the difference in electronegativity. Nitrogen as an element is more electronegative, due to which it was pulling the electrons towards itself. After protonating nitrogen, you have actually put a positive charge, and you can say out of N and N plus, who is going to pull more electrons? You are going to say that N plus will pull more electrons, or you can say the positive charge on carbon will now increase, which will actually facilitate the attack of water from the solvent. So, water will attack. Again, water is a neutral, it is attacking another species. So, after donating electron, water will get a positive charge. So, that will be OH2 positive, and since carbon has to maintain tetravalency, one of the pi bonds will move on to nitrogen. Since electrons are moving on nitrogen, negative charge should come, but there is already a positive charge. So, neutralization will happen and you will get that thing. So, here what you can do is, you can actually remove an H positive. From here, you can say one hydrogen will leave as H positive by neutralizing the positive charge on oxygen, and you will have something like RCONH OH. And what you can say here is that this H positive will then be taken by NH, or you can write it as NH2 positive. So, this hydrogen as a proton moves from hydrogen to nitrogen, which you can write it as intramolecular proton exchange. Once you exchange a hydrogen as a proton from OH to that nitrogen, again it has got a positive charge. Again this can be attacked by another water. Again pi electron will move on nitrogen. So, you will get RCOH. Again water will get a positive charge as it was a neutral attacking species. This will become NH2, this will become OH. Same way you can show an intramolecular proton exchange, that this nitrogen takes up proton and it leaves by leaving both the electrons on oxygen. So, it will be R C OH 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 NH2, and it will become NH3 positive as it has taken a proton from that side. Now, what will happen is, this will lose a proton to eliminate NH3 from the molecule, and you will get RC double bond O OH plus ammonia. Now, once again, when you look into this mechanisms are there for only to make you understand things better. Or what I am trying to tell you here is, when I am writing the mechanism, each and every step should make sense to you. You are not supposed to remember any mechanisms here. Only idea is, you should understand that that's why this H plus is going to nitrogen. If this H plus has attached itself to nitrogen, what changes it has brought into the electrophilicity of this carbon. which is then attacked by water, and because of its tetravalency, one of the pi electrons moves on nitrogen. So, if all these steps are making sense to you, you will automatically remember the mechanism, and if you are not understanding what is happening here, then you need to revise your basic concepts. So, that is how nitriles are hydrolyzed to carboxylic acid. I have already told you a shortcut how to do it. It's your choice which way you want to go. Next method will be from carbonation of Grignard reagent. So, in this particular thing, what happens is we use a Grignard reagent, let us call it as RMgX. RMgX is considered as a source of carbanion. So, while studying the Grignard reagent, what you can do is you can say that this RMgX provides us R minus for studying its reaction. For example, if I have Grignard reagent as CH3MgBr, then I know I can write it as CH3 minus. If I have PHMgBr, then I can write it as PH minus. Or if I am having CH3CH2 MgBr, then it can be considered equivalent to CH3CH2 minus. Though if you talk about the R and Mg bond, it is a highly polar covalent bond. The R carbon metal bond in Grignard reagent, though it is highly polar, but it is covalent in nature. So, that is why I am saying it is considered or it is assumed as a source of carbanion, but R minus actually is not present, but it is considered as so. So, we know if we are using Grignard reagent, what species it is going to provide us. Carbonation will be done using dry ice. So, what happens is when I use a Grignard reagent, let us say RMgX with solid CO2, which is our dry ice, then what happens here is you will result into the formation of RC double bond O minus MgX, and this can be protonated using H plus water to carboxylic acid. See, if I write the mechanism of this reaction, let me take some substrates. Let us say you are having CH3MgBr plus carbon dioxide. I will write like I know Grignard reagent is considered as a source of carbanion. So, I can say it is mainly providing me CH3 minus plus carbon dioxide structure is C double bond O double bond O. I know there is a difference in polarity of carbon oxygen bond due to which this center gets a partial positive charge and oxygens are having partial negative charge. So, in this particular case, where this negative charge is going to attack? Negative will be attracted by positive. So, I can say this will go and attack here. So, its attacking is like it is offering 2 electrons for bond formation, but carbon can maximum make how many bonds? 4. So, if it is making one new bond with CH3, it will have to break one of the existing bonds, shifting the entire pi electron density on one of the oxygen. So, can I say after the attack it will become CH3 C double bond O minus, which is similar to what we have written above. R is the CH3, CO minus is coming from CO2. Here you can write it as MgBr, as MgBr is the counterpart. This can be protonated to get your final product, which will be CH3 C double bond OH. So, if you see, if in Grignard reagent, for example, CH3 MgBr, number of carbon atom is how much? 1. But the carboxylic acid that I have formed, the number of carbon atom is actually equal to 2. So, this method using Grignard reagent with CO2 gives the carboxylic acid with 1 carbon extra, and whenever any reaction gives product with 1 carbon extra, you can actually say that you are ascending the series. Ascending the series means you have formed the higher member of that series. So, Grignard reagent reactions with CO2 can actually be used as a reaction for ascending the series or forming a carboxylic acid with 1 carbon extra. Same thing happens with nitrile also. We know that Rx is our alkyl halide. This alkyl halide, if I treat it with magnesium ether, let us say number of carbon atoms here is N. So, if I treat it with magnesium ether, it will give me Grignard reagent with number of carbon as N. Whereas, if I treat the same alkyl halide with KCN, potassium cyanide, I know it is going to give me RCN, which is alkyl nitrile, and number of carbon atom here will be N plus 1. N carbons will come from the alkyl part and 1 carbon extra from the attacking reagent. This on carbonation, that is first treatment with CO2, and the second step will be the workup step, that is protonation of the carboxylate formed, will give me carboxylic acid with number of carbons will be N plus 1, whereas nitriles can be converted into carboxylic acid by acidic or basic hydrolysis. So, here also number of carbon atoms are actually N plus 1. So, you can actually plan a reaction from alkyl halide for ascending the series. Let us say if you want your carboxylic acid to have 5 carbons, then the alkyl halide that you should start with should be with the, if that is 5, this has to be 4. Fine. So, this method can actually be employed for ascending the series. Alkyl halides can be used to form carboxylic acid having 1 carbon extra by either of the 2 methods. Next method is going to be from the acid halides and acid anhydrides. As acid halides and acid anhydrides, both are carboxylic acid derivatives. So, both of them on hydrolysis should produce carboxylic acid. Let me say I am taking RCOCl. This RCOCl in the acidic medium or in the basic medium should produce carboxylic acid. So, it should be R C double bond OH, and since medium here is basic, I already told you that in basic medium you cannot write carboxylic acid as RCOH, rather you have to write it in the carboxylate form. And this on further protonation will give RC double bond OH. So, this step is mainly known as workup step to write a neutral product from the charged ones. Again, as I said, it is the carbonyl and halogen bond which is breaking. So, as you know the electronegativity difference, halogen is more electronegative. So, this will be delta minus, this will be delta plus. I have already told you hydrolysis means break this bond. So, water you can arrange, water with its negative pole will orient towards the positive center, and this H with the delta positive, and that is how reaction will happen. You will get R C double bond O OH plus HCl. So, that is how this reaction or hydrolysis will happen. In basic hydrolysis is comparatively faster than the acidic hydrolysis in case of acid halides. Another one is anhydride. So, what you can do is, let us say if you are having R C double bond O C double bond O R. This can be hydrolyzed by just simply using water, and it will give you 2 moles of R C double bond O H. Now, let us try to understand how this reaction happens. Again, carbonyl carbon center contains a positive charge, this contains negative. Hydrolysis means break this carbonyl and the side atom part. So, what will happen here is again orient the dipoles of water H and OH. So, this will be delta minus, this will be delta positive. So, on breaking it this way, what you will get is this part will give R C double bond O will attach with hydrogen. So, OH plus C double bond O R, and this carbonyl will attach with OH. So, you will get one RCOH, another RCOH. So, 2 molecules of RCOH. If it is a symmetrical anhydride, you will get 2 moles of RCOH, but if you are having one as R1, the other one as R2, then that will be R1COH and R2COH. That depends what kind of substrate is given to you. One last method which is left is from esters. Ester is also a carboxylic acid derivatives. So, in acidic medium, we can hydrolyze an ester, and hydrolysis of esters can be done in basic medium also. And when hydrolysis of esters are actually carried out in the basic medium, that reaction is known as saponification. And hydrolysis in the basic medium is much faster than in acidic medium, because in acidic medium the hydrolysis, or you can say reaction, is reversible. So, an ester can be represented as R C double bond O O R dash. So, this ester can be hydrolyzed using H plus water and OH minus water. Since medium is acidic, again you have to break this bond only. So, this is delta minus, this will be delta positive. Hydrolyzing means put an OH here and put an H here, because that is the polarity of water molecule, and you will get R C double bond O H. That means this carbonyl part will give acid, plus OR part of the ester will result into the formation of alcohol HOR dash. So, hydrolysis of ester will produce acid plus alcohol. Whereas basic medium, since the medium is basic, it is going to first result into the formation of RCO minus plus R dash OH, and this can later be protonated using H plus water to carboxylic acid. So, if we have understood, in the methods of preparation we mainly discuss 3 from the hydrolysis of nitriles and amides, acid halides and anhydrides, and the last one we are doing is ester. These 3 reactions are actually from the basic definition of carboxylic acid derivatives, that carboxylic acid derivatives are those functional groups which on acidic or basic hydrolysis produces carboxylic acid. So, I will give you mechanism for this particular reaction, how it happens. So, I will write the mechanism for acidic medium, because basic medium is much simpler, and in acidic medium all steps are reversible. So, when I write an ester RC double bond O R dash, since reaction is done in the acidic medium, we are using H plus as a catalyst. There is a lone pair present here on carbonyl oxygen, there is a lone pair present here. You know that due to resonance that this oxygen is actually increasing electron density at this carbonyl oxygen. So, that oxygen actually has more electron density. So, if I say where this H plus will go, this H plus will go to the carbonyl oxygen, and since it is neutral, so it will become O plus H. So, arrows I made to make you understand. So, you can say it is this lone pairs which will be donated to H plus as they have more electron density. So, now what this acid catalyst does is, you see this carbon oxygen bond is polar due to the difference in electronegativity. Because of electronegativity of oxygen, it has put a partial positive charge on carbon. Can't you see now that oxygen has got a positive charge? It will be much more electronegative than the neutral oxygen. So, it will increase the positive charge more on this carbon. So, by now you should have understood one thing, that how an acid catalyst works. An acid catalyst works by increasing the electrophilicity of an electrophile. Increases the electrophilicity of an electrophile. What? An acid catalyst. When the positive charge on carbon has increased, now it is easier for water to go and attack there, and it will become this R C OH OR, and since water was neutral, you can write it as OH2. Next step is intramolecular proton exchange, where this OR group is actually going to take hydrogen as a H plus. When it leaves it as H plus, both the electrons will move on this oxygen to neutralize the positive charge. So, what will happen is R C OH OH, and this oxygen will be protonated. Now, one of the oxygens is going to donate its electron, so that this carbon will push out ROH out of the molecule. So, this will become minus ROH, and this will become RC double bond O positive H and NOH. Finally, from this molecule an H plus is lost to form the neutral product, which will be your carboxylic acid. Now, who takes out this H? There will be solvent water. Water can come and take out this H. That is not a big deal. So, this is how ester to acid you form. As I told you in the beginning itself that this is a reversible reaction, that is, if I have an ester plus I want to do its hydrolysis in the acidic medium, it will be RC double bond O H plus R dash OH. Ester, water, acid and alcohol. Now, this reaction can be made to go in the forward reaction as well as in the backward reaction. It depends on us how we maintain the reaction condition. For example, as Le Chatelier said, for this particular reaction, if you want to derive it into the forward direction, then take the reactants in more excess. So, if you want an ester to get hydrolyzed, make sure that you maintain a high concentration of or high amount of water, or ensure that as long as acid and alcohols are formed, remove it from the reaction medium. Because if you remove the product from the equilibrium, then reaction will go in the forward direction. Whereas if you want the backward reaction to happen, then you can take an excess of alcohol. So, this reaction can happen in the forward as well as backward reaction. It depends on us that how do we maintain the reaction conditions in such a way so that reaction only goes in the forward direction. So, this was the methods of preparation of carboxylic acids. Next, we can actually move on to the physical properties. So, if I talk about the physical state of carboxylic acids, then carboxylic acids up to 9 carbon atoms are colorless liquids with pungent odor, whereas higher members are wax like solids and they are odorless due to their low volatility. So, this is about the physical state. Up to 9 carbon atoms, they are colorless liquids with pungent odor. Like if you talk about the carbon 1 to carbon 4, they are having the pungent odor, whereas 4 to 9 they are having rancid butter smell, and the higher members are actually wax like solids, which makes them less volatile and one of the reasons why they are odorless. So, next thing that we can discuss is boiling point. So, now if we compare a carboxylic acid with an aldehyde ketone or an alcohol of comparable molar mass, then which one has a higher boiling point? For example, if we compare the boiling points here, then the order of boiling point will be the carboxylic acid has a higher boiling point than alcohols, which has a higher boiling point than aldehydes or ketones. Now, why carboxylic acids are having a higher boiling point? The reason given is due to the strong intermolecular hydrogen bonds. If you look into the structure of carboxylic acids, then you will find out that carboxylic acid actually exists as a dimer in the vapor phase as well as in the aprotic solvents. The dimer of carboxylic acids looks something like this. And it exists as a dimer, as I said, in vapor state and in aprotic solvent. That is one of the reasons why carboxylic acids have strong intermolecular forces of attraction and hence requires a larger temperature to break this interaction, which is actually responsible for its higher boiling point. So, remember that carboxylic acid exists as a dimer in the vapor state as well as in the aprotic solvent. Next, if we talk about the solubility, then the lower members, let us say up to carbon 4, are miscible with water, or they are soluble in water. Why? As they make hydrogen bonds with water. Anything that is to be soluble in water will have to interact with water. The way you can interact with water is either you can have dipole-dipole interaction or you should make hydrogen bonds with the water. Carboxylic acid, we know, is such a substrate which is capable of making the hydrogen bonds. So, I can say if I have R, C, double bond O, H, then if I have a water molecule, then I know there is a possibility of making this hydrogen bond. Since carboxylic acid can make hydrogen bond with the water, the lower members are soluble. But as you go higher and higher, what happens? As we go higher, the alkyl part becomes bigger and bigger. If alkyl part becomes bigger, alkyl part is actually the hydrophobic part. So, hydrophobic interaction increases, and hydrophobic is something which repels water. Since increase in the hydrophobic interaction, their solubility decreases in water. So, if you are talking about the lower carboxylic acid up to carbon 4 and all, they are completely miscible with water, whereas the higher members will have a larger alkyl chain part which is hydrophobic in nature, which decreases the solubility. Whereas carboxylic acids are soluble in less polar solvents. Less polar solvents or non-polar solvents or your organic solvents. For example, if we are having our normal solvents like benzene, chlorinated alkanes, for example, chloroform, carbon tetrachlorides, etc. You can have ethers, etc. alcohol, etc. So, this is about the solubility of carboxylic acids. Next thing that we can discuss is the chemical reactions of carboxylic acids. Now, if I make the structure of carboxylic acid, then we can divide the reactions into following types. This is the carboxylic acid. So, let us say the first reaction is when I am breaking the bond between oxygen and hydrogen. So, first reaction I can write is reactions due to cleavage of OH bond in carboxylic acid. Next reactions can be when I am breaking the bond between carbon and OH. So, this will be the second type of reactions which will be observed in carboxylic acid due to COH bond breakage. Third type of reactions will be reactions due to carbonyl part, which is C double bond O part. Let us say this part. Fourth type of reactions will be reactions due to COH group as whole. That means the reactions which will be due to this entire COH group. So, all these reactions are actually reactions due to COH group, and all these are sub part of it. The second set of reaction that we will have is reaction on the side chain or substituent, and that will happen to be the reactions which will be on this part. So, next that we are going to start is, first we will discuss reactions due to the cleavage of OH bond, which is actually related with the acidity of carboxylic acids and happens to be one of the most important topics in carboxylic acid. So, next we have is reactions involving the cleavage of OH bond, which actually shows that carboxylic acids have acidic nature. In this, the first reaction that we have is reaction with metals and alkalis. So, like alcohols, carboxylic acids also react with a metal and evolves hydrogen gas. This reaction, you can understand it as that RCOH group dissociates to give RCO minus and H positive, which is produced due to the cleavage of OH bond. Sodium, we know, as a metal will have tendency to donate electrons, and this electron is then taken up by H plus and it leaves out as hydrogen after getting reduced. So, like alcohols also react with metal and liberates hydrogen gas, carboxylic acids also liberate hydrogen with the metal, which shows their acidic nature. Like phenol, carboxylic acid also reacts with an alkali to form the corresponding salt. But there is one point of difference between phenol and carboxylic acid. This reaction is shown only by carboxylic acid. That is, when you are using a comparatively weaker base like sodium hydrogen carbonate, or let us say if you are using sodium carbonate, then only the carboxylic acid reacts with the weaker base, whereas when you use a stronger base, in this case both phenol as well as carboxylic acid reacts. Now, one thing that you can indirectly understand from this is, with the strong base both of them are able to react, but with the weak base only carboxylic acid is reacting, which kind of suggests us that carboxylic acid should have been a stronger acid compared to phenol. That is the only reason, because of its more acidity, it's also been able to react with a weaker base. Now, I am going to tell you later why carboxylic acids are stronger acids than phenol, but right now since phenol does not show this reaction whereas carboxylic acid does, this reaction is also used as a differentiating test between phenols and carboxylic acid, and that question has been asked many times in NEET. So, this is very important for you. We will understand why carboxylic acids are more acidic, but one thing you know, a weaker base like sodium hydrogen carbonate or sodium carbonate is used as a differentiating test between phenol and carboxylic acid, where carboxylic acid on reaction with sodium bicarbonate liberates carbon dioxide, which gives effervescence. What I am trying to say here is, if you have an aqueous solution which contains carboxylic acid, to this if you add 1 spoon of sodium hydrogen carbonate or bicarbonate, you will see the brisk effervescence due to the liberation of CO2 gas. Whereas, if phenol is present into this container, then on addition of sodium bicarbonate or sodium carbonate, there will be no effervescence. So, this is one differentiating test. So, what all acids shows sodium bicarbonate test. That is, they liberate CO2 gas from NaHCO3. So, let us say if I am having an acid HA, this can be any acid. The reaction between them is NaHCO3. This will be base air. If on reaction, what will happen is they will form a salt plus you will get H2CO3, which is again an acid. We know direction of a reaction is always from strong to weak. So, for this reaction to happen, this acid has to be a stronger acid and this acid has to be a weaker acid. That means any acid which is stronger than carbonic acid will actually make this reaction go into the forward direction. Try to understand, when I say something is strong or something is weak, I am only using the relative terms. When I use relative terms, I am saying carbonic acid is a weak acid compared to HA. But carbonic acid may be a stronger acid compared to something else. My idea right now is that if this reaction is supposed to go from left to right, or it has to liberate CO2, which will only be liberated if H2CO3 is formed, because H2CO3 being unstable decomposes to form water and CO2. The only way you can derive this reaction into the forward direction is only when this acid is a stronger acid than carbonic acid. So, any acid which is stronger than carbonic acid, if to its aqueous solution you are adding sodium bicarbonate, then you will get the effervescence due to carbon dioxide gas. So, now let us see what is the reason for the higher acidity of carboxylic acid. When you talk about acidity, acidity of an acid depends on the stability of conjugate base. That is, if conjugate base is more stable, its acid will be more stronger. That is, if I am talking about any acid HA, then this HA will dissociate into H plus and A minus. So, the stability, so the acidity of this acid will actually depend on the stability of this conjugate base, which is A minus. I can say, since A minus is a negatively charged species, so the stability of A minus will be directly proportional to the strength of acid, which will be also directly proportional to, in terms of electronic effects, to minus I groups, to minus hyperconjugation, to minus resonance or minus mesomeric. Or you can say the stability of A minus will be inversely proportional to plus inductive, plus hyperconjugation, plus resonance or plus mesomeric. Because stability of A minus will be directly proportional to electron withdrawing group and will be inversely proportional to electron donating group. Because stability of any charged species depends on the dispersal of the charge. No one wants to be having a charge, let it be a positive charge or a negative charge. So, A minus will be stabilized by those species which will help in dispersing its charge, and the species which will help in dispersing the charge will be electron withdrawing groups, whereas those groups which will increase charge density at a particular space actually decreases the acidity, as it decreases the stability of the conjugate base. There is another way of measuring the acidity of an acid, which is in terms of its acid dissociation constant. Here Ka is known as acid dissociation constant, which you know will be equal to concentration of products by concentration of reactant. An acid is said to be stronger acid if it produces a high amount of H plus in the solution, or an acid is said to be a weaker acid if the amount of H plus produced is low. So, we know that the acidity of an acid is directly related with the concentration of H plus it produces, and as we can see, Ka and H plus are directly related in this expression. Therefore, we can say a stronger acid has higher Ka value. Now, sometimes people find easier to compare the acidity in terms of pK value, where pK has been defined as minus logarithm of K. That is, if Ka value is 10 raised to the power minus 3 and Ka value is 10 raised to the power minus 5, pKa in this case will be 3 and pK in this case will be 5. Let us say this is an acid Ha1 and this is an acid Ha2. If pK is minus log Ka and this is the data given, I have already told you that a stronger acid has a higher Ka value, which will mean if I compare the strength of two acids, you will say Ha1 is a stronger acid than Ha2. Why? Because Ka1 is greater than Ka2. That is, a stronger acid has a higher Ka value, or if you are comparing it in terms of pK values, what you will say is a stronger acid has lower pK value. So, these things you need to remember, that a stronger acid produces a large concentration of H plus. If you are comparing it in terms of acid dissociation constant, then a stronger acid will have higher Ka value or a lower pK value. Let me just tell you the general classification which people use to categorize different types of acid. If you have a strong acid, the strong acids will have their pK value generally in the range less than 1. Acids having their pK value less than 1 are said to be stronger acid. After stronger acid, you get moderate acid. Moderate acids will be those which will be having their pK between 1 and 5. The acids which are having their pK values in between 1 to 5 are said to be moderately strong acid. Then comes the weak acids. The acids which are having their pK value in between 5 and 15 are actually weak acids. And the extremely weak acids will be the ones whose pK value is actually greater than 15. So, this is the general idea that you should have. Once you look at the pK value, you should be able to tell whether it is a strong acid or an extremely weak acid. This will help you. Now, I will write pK value for some acids which are given in your NCERT and will give you an idea about how stronger or how weak your acids are. For example, if I talk about trifluoroacetic acid. I will write nearly approximate values, they can change a bit. The pK value of trifluoroacetic acid is nearly 0.23. If I write benzoic acid pK value is nearly 4.2, or the value given in your NCERT is 4.19. Acetic acid pK is somewhere around 4.76. If you talk about inorganic acids like hydrochloric acid pK value is -7. This is an inorganic acid and these are all organic acid. You can say that inorganic acids are stronger than organic acids, and out of the organic acids available, carboxylic acids happens to be the one of the strongest acid. Within carboxylic acids, trifluoroacetic acid happens to be one of the strongest acid known. Other ones which you can remember is, for example, phenol. Phenol pK value is around 10. Whereas, if you are comparing the pK values of an alcohol, or let us say for an ethanol, their pK values will be somewhere around 16. And water pK value is also somewhere between 15 to 16. So, these pK values are actually going to give you a rough idea how to compare the acidic strength of different acids. As you can see here is that carboxylic acids and phenol, which has a lower pK value, carboxylic acid, and they are stronger acid than your phenol. We will discuss just now like why phenols are less acidic. But first of all, let us say what happens to a carboxylic acid when it is put in water. So, when you put it in water, carboxylic acid loses its H positive, this is K equilibrium, and forms RCO minus plus H3O positive. If I write its K equilibrium, it is going to be the concentration of RCO minus H3O positive divided by RCOH into water. Since water is a solvent here, its concentration can be assumed to be practically constant, and that is why K equilibrium into water is assumed to be a new constant which is equal to Ka and is said to be acid dissociation constant, whose value will be equal to RCO minus into H3O plus divided by RCOH, or we can say higher the K value, stronger the acid, lower the pK value, stronger the acid. Now, one more thing that we said is, if this is carboxylic acid, we said acidity of any acid has to be related with the stability of its conjugate base. That means, if carboxylic acids are moderately strong acids, somehow their acidity is related with their stability of conjugate bases. If I write the structure of conjugate base of carboxylic acid, which is a carboxylate anion, what I observe here is that this carboxylate anion is resonance stabilized, where negative charge so produced can be stabilized on other oxygen as well. So, this is resonating structure 1, this is resonating structure 2. Due to delocalization of negative charge carboxylate anion produces two equivalent resonating structures, and these two equivalent resonating structures are what is actually responsible for the stability of carboxylate anion, which in turn is responsible for the acidity of carboxylic acid. We know resonating structure 1 and resonating structure 2. Using these two, we can write a resonance hybrid, in which you can say that both the oxygen, the negative charge is dispersed over both of them. So, this will be the resonance hybrid. So, the reason for the acidity of carboxylic acid is actually the stability of its conjugate base, which happens to be resonance stabilized, and the resonance stabilization happens in such a way so that the negative charge actually gets stabilized on both the cases on oxygen alone. Next, we are going to compare is why carboxylic acids are more acidic than phenols. For example, if I have phenol, I have to decide the acidity of phenol again on the basis of stability of its conjugate base. So, if this is my acid, this will be my conjugate base. Now, I have to see what are the factors stabilizing this conjugate base. Then you will say, sir, due to resonance, this negative charge can be delocalized on the benzene ring. If I do the delocalization of this electron density, then I can write this as one of the resonating structure. This can be further delocalized. And that resonating structure will be this. This can be further delocalized. And then another resonating structure will be this one. So, we have resonating structure 1, resonating structure 2, resonating structure 3, resonating structure 4 and resonating structure 5. We know that if the conjugate base can be stabilized by resonance, it increases the stability. We can say that the negative charge is stabilized in carboxylic acids as well as in phenol by resonance. We have also learned that if more the number of resonating structures, more will be the stability of conjugate base, which will make you inclined to give an answer as phenol, as you will say, sir, in this case more resonance happens, more number of resonating structures are there, so phenol should be more acidic. But that is not what you have to follow. One of the other rules of resonance says that if by doing resonance, if you can make equivalent resonating structures, then the stability of those resonating structures are more. As you can see, in resonating structure 1 and resonating structure 2, the bond connectivities are all same. What I mean is, in this case oxygen carries a negative, in this case also oxygen carries a negative. There is a C double bond O, there is a C double bond O. Whereas the resonating structures in case of phenoxide are not equivalent, as in one case oxygen carries a negative charge and the other case carbon carries a negative charge. So, you can say resonating structures in case of carboxylate anion are more stable as they have equivalent resonating structure, first thing. Second thing is, as both of them are stabilized by resonance, resonance says that if negative charge can be stabilized by resonance, it increases the stability of conjugate base. But it increases the stability of conjugate base even more if that negative charge can be delocalized on more electronegative atom, as more electronegative atom will stabilize a negative charge better. That is why if you see in this case O minus and O minus, if the total charge is 1, half of this charge is stabilized by this oxygen and half is stabilized by the other oxygen. So, after resonance also I have put negative charge on more electronegative atom, whereas in this case only a fraction of negative charge is carried by oxygen whereas in these resonating structure, the atom that is carrying the atom that is carrying the negative charge is actually carbon, which is actually a less electronegative atom. And the stability of negative charge on more electronegative atom is more compared to the same negative charge on a less electronegative atom. And that is the reason why, since the conjugate base of carboxylic acid is more stable than phenol, carboxylic acids are more stronger acids than phenol. Next thing we have to discuss how the acidity of carboxylic acids will be affected by change in the nature of this R group. How acidity will be affected when R will be an electron donating group or R will be electron withdrawing group is something we will discuss next.